Hi everyone, welcome once more to this channel, Best Science Brain YouTube channel. Today we are taking another chemistry content on general chemistry for Phase A students and A-level students. This topic is also essential for those who are in the final years of high school or secondary school. So we're going to teach from the scratch of this topic to the end of the topic. So the aspects we're going to cover include chemical bonding, the different types of chemical bonding, illustration of chemical bonding, valence bond theory, hybridization, bond properties, lattice energy, geometry or shape of simple molecules, and so on. So that'll be our focus in today's lecture. So we're going to take a comprehensive look on chemical bonding. So today we'll start by defining chemical bonding. We'll say chemical bonding is a combination of atoms to produce stable molecules, compounds, or ions. The combination of atoms to produce stable molecules, compounds, or ions. This is what is known as chemical bonding. So in chemical bonding, molecules, compounds, or ions usually satisfy the duplet or octet state. So during chemical bonding, the molecules produced, the ions formed, or the compounds produced usually satisfy the duplet or octet state. So are there molecules that do not satisfy the duplet or octet state? Yes. There are molecules that do not satisfy duplet or octet state even after bonding. We're going to look at the deviation from the octet or duplet rule later on in this topic. Then what is the duplet rule all about? The duplet rule specifies or states that an atom with only K shell is stable when the K shell has 2 electrons. An atom with only K shell will attain stability when the K shell has only 2 electrons. Now in chemistry, there's only one atom which satisfies the duplet state, and that atom is called helium. So helium is the only atom in duplet state. Why did I say so? The atomic number of helium is 2. If you go to the electronic coefficient of helium, we have, using the shells, we have 2 under the K shell. So meaning that helium has only K shell, and then helium, that K shell takes 2 electrons, meaning that helium satisfies the duplet. The duplet refers to 2 duplet state. The only element during chemical bonding that can satisfy this state when it combines with other atoms. I repeat, the only element that can satisfy or assume the state of helium when it combines with other atoms is hydrogen. Hydrogen atomic number is 1, and it has only 1 electron in the K shell. So the 2 elements that have K shell in the periodic table are helium and hydrogen. Helium is already in the duplet state, while hydrogen requires 1 electron to make it up to 2 to satisfy the duplet state. For hydrogen to satisfy the duplet state, hydrogen will now undergo covalent bonding or chemical bonding so that it will have 2 electrons in the K shell. Having understood the duplet rule, we now look at the octet rule. Octet rule. The word octet refers to 8. Octet rule specifies or states that other elements apart from helium are stable by having 8 electrons in their outermost or valence shell. So that is octet rule. So the elements that are in octet state are other noble gases: neon, that is 10 electrons, future electrons, K shell takes 2, remainder 8. Please go to L shell. We also have argon, 18, KLM. K shell takes 2, remainder 16, L takes 8, 8 plus 2, 10, remainder 8. So the outermost shell of neon is having 8 complete. That of argon is also having 8 complete. So these 2 elements are in octet state. So when we talk about octet state and duplet state, these are the rules obtained from elements we call noble gases. Noble gases are helium, neon, argon, xenon, krypton, and so on. Helium certifies the duplet state, while other noble gases tend to certify the octet state. So these elements are stable and they don't normally undergo chemical combination or bonding because their outermost shells are filled up. This has 2 in the K shell, this one's assumed to have 8 in the outermost shell. Now, other elements are positively jealous of them. What do I mean by that? Other elements want to be like them because they don't have complete outermost shell. Look at sodium, 11, KLM, 281. Incomplete in the outermost shell. Look at chlorine, 17, KLM, 28, remainder 7. So these other elements are reactive because the outermost shells are not complete. So they tend to come together. When they come together, they want to now, after coming together, form molecules or to form compounds. They will now tend to achieve the complete outermost shell. Octet state. So during chemical bonding, hydrogen is the only element that attains duplet state of helium, while other elements like sodium, chlorine will now tend to attain the octet state of other noble gases. So when we say duplet and octet rule, refer to rules governing noble gases. Noble gases appear to be stable under ordinary conditions. Other elements tend to become like noble gases when they combine with themselves or when they combine with another element. And then when they do that, they will now tend to have the octet state and duplet state certified and be like noble gases. So that's the essence of chemical bonding. Before we go on, we have to point out something. We should know that chemical bonding occurs in the valence shells and involves the valence electrons. So chemical bonding does not involve all the electrons the atom has. Chemical bonding only involves the valence electrons. Valence electrons, the word valence means outermost. If I say valence shell, it means the outermost shell. If I say valence electron, it means the outermost electron. For instance, look at sodium. Write the electronic coefficient by using the shells. We have 2, remainder 9. This one takes 8, remainder 1. Now for sodium, this M is the valence shell of sodium. The M shell, the last shell. While for sodium also, this one is the valence electron. So sodium has one valence electron and then M at the valence electron. Look at chlorine, 17, 287. So for chlorine, the valence shell is also this M shell. While the valence electron, chlorine has 7 valence electrons. So chemical bonding involve, okay, let me take an example. Look at calcium, 20, K2, L8, M8, and N2. For calcium, N is the valence shell, and calcium has 2 valence electrons. So chemical bonding will occur in the atomose shells. So when atoms are combining together, they use their atomose shells, and then it will involve only the valence electrons, electron found in the atomose shells. So having done that, we'll now go over to identify metals and non-metals. Before we go into the different types of chemical bonding, we have to identify metals and also identify non-metals, especially in the first 20 elements. So what are metals? From the whiteboard, metals are elements that donate their valence electrons to produce positive ions. That is why metals are called electron donors, or call them electropositive elements. Second sentence says metals do not have more than 3 valence electrons. So this is one of the ways to know that an element is a metal. Metals do not have more than 3 valence electrons. So let's look at a few examples we have on the board. Lithium, the number is 3. If you share electrons, we have 2, 1 under the K and L shell. The valence shell for lithium is the L shell. The valence electron lithium has is 1. So go to sodium, 11, 2, 8, 1. 2 under the K shell, 8 under the L shell, 1 under the M shell. The valence shell is the last shell, that's the M shell. Valence electron for sodium is still the same 1. Going to magnesium, 12, 2, 8, 2. Share it under the K, L, and M shell. The valence shell is the M shell, and the valence electron is 2, the electron in the atomose shell. Aluminium, 13, 2, 8, 3. So M shell, the atomose shell for aluminium. Valence electron is also the same 3. Potassium, 19, 2, 8, 8, 1. It has 1 in the N shell. So the N shell, the valence shell, and the valence electron is only 1. Calcium is 20, 2, 8, 8, 2. It has 2 in the N shell. So valence shell is the N shell, the valence electron is 2. So you can see that from the valence electrons we have here, none of them is more than 3. And that makes the elements metals in the first 20 category. Now, are there elements that have 1 to 3 electrons that are not metals? Are there elements that have less than 3 or not more than 3 in the atomose shell, but they are not metals? Yes. There are some examples in the first 20 series. Hydrogen is having only 1 in the K shell. But hydrogen is a non-metal because it possesses non-metallic properties. Then helium is to also have 2 in the K shell. It's also another non-metal. So these are 2 examples of elements that do not have up to 3 electrons in their atomose shell, but that classify as non-metals. Another example is boron, having 5, 2, 3. So boron is having 3 in the atomose shell, and from the electronic structure of boron looks as if it's a metal, but boron is not considered a metal. Boron is a metalloid. A metalloid is an element that possesses both metallic and non-metallic property. So these are a few examples of elements that we see they do not have more than 3 valence electrons, but are considered as either non-metals or, in the case of boron, metalloid. So we're going to look at how to define non-metals now, and then give some examples before we move to the different types of chemical bonding. So on the whiteboard, we have identification of nonmetals. So what are nonmetals? Nonmetals are elements that accept electrons to produce negative ions. That's why in chemistry, nonmetals are called electron acceptors or electronegative elements. So continuing, nonmetals mostly have more than 3 valence electrons. As we said before, metals are defined by having not more than 3 valence or atomos electrons, while nonmetals have more than 3 valence electrons. So let's look at specific examples. Carbon, whose atomic number is 6, shared electrons under the K and L shell have 2, 4, and that 4 is in the L shell. So the valence shell of carbon is L, and the valence electron of carbon is 4, which is under the L shell. The second example, nitrogen with atomic number of 7. The electronic configuration is 2, 5. So the valence shell is L shell also. The valence electron is 5. Oxygen, 8 electrons, sharing it 2 under the K shell, 6 under the L shell. The valence shell is L shell. Valence electron is 6. Phosphorus with 15 electrons, 2, 8, 5. That 5 resides in the M shell. So valence shell is M shell, valence electron is 5. Sulfur 16, 2, 8, 6 has 6 electrons in the M shell. Valence shell is M shell, valence electrons is 6. Argon 18, 2, 8, 8 having 8 electrons in the M shell, so valence shell is M shell, valence electrons is 8. So look at the valence electron column. You have 4, 5, 6, 4, 5, 6, 5, 6, 8. The valence electrons of these elements we have here are all more than 3. That means the elements we have on the board are non-metals. So having done that, having understood the concept of metals, how to identify metals and how to define non-metals, we'll now go to the types of chemical bonding. So on the whiteboard, we have the major types of chemical bonding we have in chemistry. The first type is called ionic bonding. So either you call it ionic bonding or you call it electrovalent bonding, or you can call it electrovalency. Number 2 is called metallic bonding. Number 3, covalent bonding, or you can still call it covalency. Number 4, coordinate covalency. You can still call it coordinate covalent bonding, or you can call it dative bonding. So these are the 4 major types of chemical bonding we have in chemistry. We shall now start discussing them one by one and give illustrations for each of them. So we're going to start with ionic bonding. So we'll now look at the key concepts of ionic bonding. I'll have them itemized on the board. So what is involved in ionic bonding or in electrovalency? Number 1, it involves electrostatic attraction between positively charged metallic ions and negatively charged non-metallic ions. It occurs between metals and non-metals. So now number 1 is pointing out that ionic bonding must occur between a metal and a non-metal. Any compound that contains a metal and a non-metal, for example, sodium chloride, sodium is a metal, chloride is a non-metal. Calcium oxide, calcium is a metal, oxygen is a non-metal. So any compound that involves a metal and a non-metal contains ionic bond. Number 2, it involves complete transfer of valence electrons from metallic atoms to the non-metallic atoms. So during ionic bonding, the metal will transfer its valence electrons to the non-metal. Number 3, at the end of ionic bonding, metals produce positive ions and non-metals produce negative ions. Since we say that ionic bonding involves transfer of electrons from the metals to non-metals, when a metal loses electrons, it becomes positively charged. I will call that positive charge, we'll call it a cation. Then when a non-metal accesses electrons, it becomes negatively charged, and we'll call that ion of a nonmetal. The negative charge, we'll call it an anion. Number 4, it occurs between atoms of large electronegative difference and makes the bond polar. So since the elements involved are in ion bond are metals and non-metals, and you know in the periodic table, metals normally stay at the left-hand side of the table, while non-metals are found at the extreme right-hand side of the table. That means these elements have wide difference in the electronegativity, metals being electropositive and non-metals being electronegative. So when you have two elements that one is electropositive and the other is electronegative, we say that they have large difference in the electronegativity, and such bond is polar. So that is why most ionic compounds dissolve in water. So having done that, so what are examples of compounds that have ionic bond inside them? As I said, like sodium chloride have a metal and a non-metal. We have defined metals today. Calcium chloride, sodium bromide, calcium oxide, magnesium chloride, magnesium bromide, lithium iodide, lithium chloride. So copper oxide. You can continue naming as many as barium chloride, barium oxide, and so on. So if you look at them, zinc oxide, you look at them, you see that all these compounds contain a metal and a non-metal, metal and non-metal, metal, non-metal, metal, non-metal, and so on. So all these compounds contain ionic bond inside of them. So now, before we go into ionic bonding proper, we're going to now go into illustration of ionic bonding. Before we learn how to illustrate ionic bonding, we're going to use a method called the Lewis method to illustrate bonding all throughout this video. We're not going to the share method for proximity and accuracy. We're going to use the Lewis electron dot method. So I'll highlight on the Lewis method in a few seconds now, and then we'll now go to illustration of ionic bonding and illustrate how ionic bond occur in some of these compounds. So we have Lewis electron dot method. This is a method introduced by a man called Gilbert Lewis in 1916. So this method supersedes the drawing of shells introduced by Bohr or Niels Bohr in 1913. So Lewis gave us a format to present atomic structure or electronic structure. So we call it Lewis electron dot method. It's a very simple thing and very simplified compared to the Bohr's method. For instance, when I have sodium, the electronic configuration of sodium is Kl281. In the Lewis method, our focus will be on the outermost electron of the element, since we say that bonding occurs in the outermost shell and involves the outermost electron. So in the Lewis method, you don't have to start drawing circles or shells. What we do is write the symbol of sodium, Na, and you're going to present only one electron with a dot. So that is the Lewis structure of sodium atom. So sodium symbol and the electron, that electron for sodium, that's only one. You only represent the atom's electron. If I use chlorine, for instance, 287, I want to show the Lewis electron structure of chlorine. I'll have chlorine, so electrons in the atmosphere shell have 1, 2, 3, 4 along the 4 cardinal points. 1, 2, 3, for remaining 3. I'll start pairing. 5, 6, 7. So I have 3 paired electrons and 1 unpaired. So this is the Lewis structure of sodium atom. Perhaps if I have oxygen, 8, Kl2, For oxygen, I'll have this. I'm going to present only the atoms electron, which is 6. I have 1, 2, 3, 4. Remaining 2. I'll pair any 2. Then maybe this and that. That is the Lewis structure of oxygen atom. So that is a very simple thing to understand. Lewis structure. If it's nitrogen, for example, 7, Kl2, 5. I'll present only the atom's electron, that is 5. 1, 2, 3, 4. Remainder 1. I want to pair any 1. maybe this one here giving us 5 electrons around nitrogen. So that the concept we were applying to illustrate bonding, the Lewis electron dot method. So having done that, we go back, we switch back to illustration of ionic bonding. So we'll go to illustration of ionic bonding. So the first example I will use here is the simplest of the compound, sodium chloride. So how do we illustrate ionic bonding in sodium chloride? So what I'll do is I will split this into the component atoms. There are two elements here, sodium and chlorine, and two atoms, one of sodium and one of chlorine. So I have Na plus Cl. Having done that, I'll now write the electronic configuration of each of the atoms. Sodium atom number is 11. I have KLm287. One is 17. KLm. So this is 281 for sodium, 287 for chlorine. Having done that, I'll now draw the Lewis structure for each of the atoms. Sodium, our focus is the atom's electron, which is 1. Chlorine, 7. I can use the same dot or I can use asterisk so that I can mark a difference. So 7, I've drawn 4, remaining 3. I will now pair this, giving us 7. So you see that's the Lewis structure. You know that sodium is a metal by virtue of having not more than 3 in the atom's shell, and chlorine is a non-metal. And the bond between them is ionic bond. In ionic bonding, as we described earlier, the metal will donate all of its valence electrons to the non-metal. So if an electron of sodium is 1, you're going to donate this one to chlorine, which requires 1 to become complete. So this one electron from sodium, you draw a curved arrow showing that it's moving from sodium to chlorine. So at the end of bonding, you draw another structure. Sodium again, this time around. Sodium has lost the 1 electron in the M shell, meaning that the M shell is now empty. The atom's electron for this sodium now becomes 8 because this one has gone off. You now show 8 electrons around sodium. Okay, they will still go 1, 1, or if you do it 1, 1 or 2, 2, it will still give you 8 electrons. You can see that. So 8 now residing in the atom's shell of sodium. And then when sodium has lost electron, it becomes an ion. So you now circle it and put positive charge, showing that it has lost 1 electron. It's now an ion, otherwise called cation. Then for chlorine, chlorine has accepted 1 electron from sodium. You see, draw it again, the structure will change. Have the electron up there, the other up there, down there, and then have 1 from sodium going to chlorine. So 1 dot and 1 asterisk. This one came from sodium. You see, chlorine has accepted, and when a nonmetal accepts, it becomes negatively charged. You put minus, it accepted only 1 negatively charged. So we call this an anion. Now if you look at sodium, the electronic structure of sodium ion, this is not, look at the difference. This has no charge, but this has a charge. This one is now 2, 8. That is having 2 and 8, no longer 2, 8, 1 as before. So it looks more like the element called neon. Neon, whose atomic number is 10, noble gas. While this one has setted 1 to make this one up to 8, 1 becomes 2, 8, 8. Looks more like an element called argon. So you can see that. So this is an illustration of ionic bonding in sodium chloride. I want to take another example of this. Number 2, I'll use calcium chloride, or rather let me use calcium fluoride. You change the elements. Calcium fluoride. So you look at it, this is an ionic compound containing a metal and a non-metal. So in this compound, there are 2 elements, calcium and fluorine, but there are 3 atoms. 2 elements, calcium and fluorine. There are 3 atoms, 1 of calcium and 2 of chlorine. Atom means the frequency of the element in the compound. So 1, 2, 3. So I'm going to write 3 symbols, 1 of calcium and 2 of chlorine. But I have to first of all ask myself what the central atom. The central atom there is the atom that is the element that has only one atom, that is calcium. So calcium being have one element will be at the center. So fluorine will be on this side, one will be on the other side. So the electronic configuration of chlorine is 2, 7, having 9 electrons as its atomic number. The same here 2, 9. Calcium has atomic number of 20. So the electronic configuration is going to be 2882. So the next thing we do is to draw the Lewis structure of each of the atoms. So fluorine has 7. Have 1, 2, 3, 4, 5, 6, 7. That is fluorine. I can still draw the brother over there. 1, 2, 3, 4, 5, 6, 7. That is the same fluorine. Then calcium at the middle has only 2 electrons in the outermost shell. I'll put one by this side and one by the other side for easy donation. Now we look at the structure of the elements. Calcium is a metal, not having more than 3 in the outermost shell. Why these two 7 please? Why these 2 are non-metals? So calcium will donate 2 away. A metal donates everything in the atmosphere away. But that 2 cannot go to 1 fluorine. Because if you go to 1 fluorine, chlorine will now become more than 8, so violating the Octet rule. So fluorine requires 1, being a non-metal. This one requires also 1. So for these 2 now, it means that for fluorine to attain Octet state, 8, 8 here, 1 of the electron from calcium will go to this one, 1 will go to the other fluorine atom. So we use a coiled arrow, put the arrowhead to show where it is going. So having done that, you see that our calcium now will now have Ca. Calcium has 2 electrons given out. So the N shell becomes empty. The outermost electron becomes 8. We'll have 8 electrons in the outermost shell. So you can just make them 2 at once without waste of time, making it up to 8, already complete. And after a metal has donated, it becomes charged. You have to show the charge. And the charge becomes positive charge, positive 1 or positive 2. You have lost 2, so the charge becomes positive 2, 2 plus. That's the cation of calcium. Having now 2, 8, 8, looking more like argon, 18 electrons. So for fluoride ion, each fluorine atom has accepted 1 electron. You can see that each other is taking 1, 1. So now I have 2, 4, 6, and then of course 8, with 1 coming from calcium. You see that is the fluoride ion. Of course, what remains is to put a charge on it. So how many electrons did it accept? It accepted only 1 electron. When I put minus here, that's 1 electron. You can still draw another 1 by the side here, or if you are drawing only 1, since the 2 are the same, you just put 2 in front to show there are 2 of fluoride ions, of fluorine atoms that form fluoride ions. So it's not repeating this again. So the EC becomes 2, 8 for each of them after accepting 1. So this is now an anion. So you see an illustration of ionic bonding. We'll take one more example on this ionic bonding. And the example is we have sodium oxide, Na2O. Sodium oxide. So sodium is a metal, oxygen is a non-metal. So the bond there must definitely be ionic bonding. So having done that, we see that there are 2 elements here, sodium and oxygen. But there are 3 atoms, 2 of sodium and 1 of oxygen. So I'm going to write the symbol of 3 atoms. But before I do that, I'll ask myself which of the atoms will be the central element. The one that contains only 1 element, which is oxygen, be at the center of this Na and then Na. So you write the electronic configuration of each of them. So it's 11. So I have 2, 8, 1. The same thing for this one. 2, 8, 1. Oxygen, atomic number of oxygen is 8. So we have 2, 6. So we draw the Lewis structure for each of them. In this case, now the non-metal is at the middle. Well, it doesn't matter whatever is at the middle. Just understand the concept these two are metals and they must lose electrons in the outermost shell. While this one is a non-metal, you're going to accept. So we have sodium, one electron in the outermost shell, and that sodium on the other side, one electron in the outermost shell. Also in the middle, with 6 in the outermost shell. Let's draw it 1 with asterisk, 2, 3, 4, 5, and then 6. So you see that. That shows that the metal will lose. If the metal has 1, the 1 will go off. It has 2, it will lose the 2. And it has 3, it will lose the 3. But the metal will accept. This one needs 8 to become complete. So extra 2 is required. So that extra 2 won't come from this sodium. The one will come from the other sodium. You can see the arrow. At the end of the day, sodium will now become, having lost 1, the M shell for each sodium becomes empty. What will now be in the outermost shell is the L shell having 8. 1, that is 2, 4, 6, and then 8. Sodium is a metal. When you accept, it becomes positively, when you lose, it becomes positive charge, like +1, having lost 1. So, and then we'll put 2 to show there are 2 sodium atoms involved. Then oxygen accepted 2. We'll have this, we'll have that, and then we'll have this. So taking 1 from this sodium and take 1 from the other sodium, making it up to 8. So you now have this, bracket it, again 2. You now write 2 negative at the charge. So this is the cation, this is the anion. So the EC is now 2,8 after losing 1 for each of the sodium. This one becomes 2,8 after accepting 1 or 2 from the 2 sodium atoms. So you see that the essence of bonding, at the end of bonding, the ions formed, each of them will be in octet state, having 8 electrons. The metal will lose all of its atom's electron and still have 8. While the nonmetals will accept to make it up to 8 as well. So this is the concept of ionic bonding. Having done that, move over to another thing. So we'll look at the characteristics or general properties of ionic compounds. The first characteristic says they are crystalline solids of high melting points. Their high melting points is due to the strong electrostatic attraction between the metallic cation and non-metallic anion. So ionic compounds have high melting points. Let's think of sodium chloride, which we use for as illustration. In sodium chloride, have sodium ions bonded to each sodium ion bonded to a chloride ion. Sodium ion again, chloride ion. Here, chloride, because it should be on like charges together. Sodium, chloride, sodium. Under there, sodium ion, chloride. Then sodium, then chloride. So this is a sodium chloride crystal lattice we're trying to represent on the board. So you see that in that example we have sodium attracted to chloride. So you see the attraction between charges or unlike charges is called electrostatic attraction, and that constitutes the ionic bond. It's a strong bond because it's not easy to separate these ions unless you use high amount of heat energy. It's when the bonds break, then that you have to see the substance collapse and melt. That is why they have high melting points as indicated in number 1 property. Number 2 says ionic compounds are polar. Polar means that they are formed from elements of wide difference in electronegativity. They have dipole moments. So polar means they are soluble in water or in polar solvents. Ionic compounds dissolve in water. So number 3, ionic compounds consist of aggregate of ions, cluster of ions. That is, if you look at them, you see the ions are all clustered together. So they are joined, the ions join together. So number 4, ionic compounds, aqueous solutions of ionic compounds are electrolyzed. Aqueous solutions or any compounds are electrolytes. 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 Electrolytes are solutions that conduct electricity. Aqueous means when they dissolve inside water, they will conduct electricity. Because when they dissolve inside water, the ions will now migrate freely on their own and they will now conduct electricity. So these are the major properties or characteristics of ionic compounds. I have a question on the board that says, explain why aqueous sodium chloride conducts electricity, but crystals of sodium chloride do not conduct electricity. Remember that the word aqueous means when it dissolves in water, it conducts electricity, while the crystals means in solid state, it does not conduct electricity. Why is this so? Because in aqueous state, sodium chloride ionizes or dissociates into positive, which is sodium ion, and negative chloride ion that are mobile. So in aqueous state, this compound will break into, when dissolved in water, break into sodium ion and free ion that can move around. So unless the ions are free to move, they cannot conduct electricity. So that's why in aqueous state, it conducts electricity. But in crystals or in solid state, the ions are aggregate or immobilized and form aggregates. In crystal state or solid state, the ions are just connected to each other, bonded. So there are no freedom of movement. Immobilized, they are not moving. So they cannot conduct electricity in this form. Aggregate of ions. So they can't dissociate in this form. So that is why in aqueous state, any compound can conduct current because it can ionize. But in solid state, any compound cannot conduct because it consists of immobile ions. So that is the reason for this. And that answers the question. So now we're going to look at the Born-Haber circle, which is a station of ionic bonding. The Born-Haber circle is a thermodynamic circle used to calculate the lattice energy of an ionic solid. I repeat, this is a thermodynamic circle used to calculate the lattice energy of an ionic solid. What is lattice energy? Lattice energy is the energy released when 1 mole of an ionic compound is formed from its constituent ions in gaseous state. For instance, if I wish to produce sodium chloride is obtained from sodium ion and chloride ion in gaseous phase. So you now have sodium chloride produced from its ions. So the energy required to produce 1 mole of sodium chloride ionic from its gaseous ion is known as the lattice energy. Let's call it L, the lattice energy of sodium chloride. And in that formation, the energy is released. So lattice energy is negative because energy is given out. It's an exothermic process. So formation of ionic compound is an exothermic process. That the lattice energy is always negative. So we can call it S joules or minus S kilojoules, as the case may be for this substance. So let's go back. We say Born-Haber circle is based on the Hens law of constant heat formation. So the Born-Haber circle is based on a law called a law derived by Hens called the Hens law of constant heat formation. So what does Hens law state? It states that the sum of the total enthalpy change for a reaction is the sum of the individual steps into which the reaction can be divided. Hence, law states that the sum of the total enthalpy change for a reaction is the sum of the individual steps into which the reaction can be divided. So for us to understand Born-Haber circle and how to use it to derive lattice energy or to calculate that energy, we're going to look at the steps involved in Born-Haber cycle. Born-Haber cycle normally involve 5 steps, which normally include sublimation, dissociation or ionization, electron affinity, and so on. So we're going to lead the 5 steps involved in Born-Haber cycle, and then look at the cycle, and then look at how we can use it to do calculations. So as we said that there are about 5 to 6 steps involved in Born-Haber cycle, and then we have itemized 3 steps on the whiteboard, and then we're going to itemize the remaining 3 or 2 steps after this. The first step involved in Born-Haber cycle is sublimation of the metal. To sublime means to move a solid to gaseous state. Sublimation of the metal. So that's the first step involved in Born-Haber cycle. So we say this is a process. This process requires the enthalpy of sublimation. The heat energy required here is called the enthalpy of sublimation that's required to sublime 1 mole of a solid to 1 mole of this gaseous state, from solid state to gaseous state, changing the metal M from 1 mole to also 1 mole from solid to gaseous state. Example, using sodium. Sodium in solid state transformed to gaseous state will now require the enthalpy of sublimation, which is written as delta H SUB. Sublimation enthalpy is a positive value. Then the next step also that is involved in the Born-Haber cycle is ionization of the metal atom. Ionization is the process of removing an electron. So this involves the removal of 1 mole of electron from a mole of the gaseous atom to produce 1 mole of a univalent gaseous ion. So when the metal has been sublimed from solid to gaseous state, the next thing is that the gaseous metal or the metal in the gaseous state will now become ionized by losing 1 mole of electron to produce 1 mole of univalent ion. Ion in the positively charged univalent gaseous ion. So energy required to do this process is called the ionization energy, IE. It's also a positive energy. So it's also positive energy. So the third step we have here is dissociation. Dissociation of the non-metallic molecule. Remember that an ionic compound contains a metal and a non-metal. So we'll talk about dissociation of a non-metallic molecule. So dissociation, we need what's called a bond dissociation energy. So this is the energy required to dissociate a diatomic molecule into its constituent ions in the gaseous phase. So you can see S2 is the molecule, which could be a non-metal like chlorine. So Cl2. We are producing 1 atom of it in the gaseous state. So to balance the equation, S2, to have only 1 atom, you have to put half here because half times 2 gives you 1. So example, if I use chlorine molecule, I have half Cl2 giving me Cl gas. So the energy required to dissociate the chlorine molecule or half mole of chlorine molecule to 1 atom of chlorine is the dissociation or bond dissociation energy, which is also a positive value here. So we now go to the other types of energy required or processes required in the Born-Haber cycle. So how the remaining 3 steps or 3 energies involved in Born-Haber cycle. The fourth one is the one we call electron affinity, EA. This is the energy released when an electron is added to a gaseous atom to form an ion. Remember in the third step we did was electron dissociation energy, where we'll produce a gaseous non-metallic atom. So when the gaseous non-metallic atom produces the third step gains an electron to produce a negative ion, the energy required here or released in this process is called electron affinity of that reaction. So that is called electron affinity. And electron affinity is the negative energy because it's released. So it's a thermic process. So it's negative. So number 5, we have the lattice energy, L. The energy released when 1 mole of ionic solid is produced from its constituent ions. So the ions from the metal is M plus, the ion from the non-metal is S minus. So this one is produced from electron affinity process. The one is produced from ionization of the metal, step 2 or thereabout. So when you add the ions produced in these two steps, you get the energy required to form one more of a compound from its gaseous ions. In gaseous ions is what's called the lattice energy. And the lattice energy is also negative in value. Then the sixth energy in this process is called the enthalpy of formation, delta HF. We study the enthalpy change when one mole of a compound is formed from its constituent atoms. We're forming one mole of sodium chloride from sodium and chlorine. So sodium chloride contains sodium and chlorine, so have sodium to balance the equation. Since you need one mole of sodium chloride here, we have to put half here so that we'll have half times 2 giving us 1. So we'll have 1 atom of chlorine so that it will give us 1 mole on the product side. Because if we shouldn't have half here, if we actually put 2 thereabout, I'll have 2 moles. And that'd be wrong because enthalpy of formation deals with production of 1 mole of the substance. So if this here should be 1 mole, we have to put half to counter these 2 to balance the equation. So having done that, we're now going to draw the diagram for Born-Haber circle. So we'll go to the diagram for Born-Haber circle. So how do we go about the diagram? Let's consider formation of sodium chloride. Sodium chloride is formed by combining the elements inside sodium chloride, which is sodium and chlorine, giving us 1 mole formation of sodium chloride, 1 mole of sodium chloride. So have 1 mole here, I have to balance the equation by putting half here. Half times 2 gives us 1. So we'll now get 1 mole. The energy involved in this making of 1 mole of sodium chloride from this is the enthalpy of formation. So we'll now write Na plus half Cl2. You draw a long arrow. And then on the product side, you write NaCl. So forming sodium chloride from the constituent elements. So what we need here is delta HF, which is the enthalpy of formation, forming sodium chloride from its constituent elements. Then after we have done that, we'll talk about sublimation. That's the first step we'll talk about. Sublimation of the metal. So this metal becomes sublime. You draw an arrow downwards to show when you hit the metal, that's the first step I gave you. When you hit the metal, it turns to gas. Look at the difference, solid to gas. We now need the enthalpy of sublimation, SUB, to move the metal from solid state to gaseous state. The next step I also talk about is the enthalpy of dissociation, and that should be step number either 2 or 3. Dissociation of the ionization of the metal, step number 2. Ionization energy. So I told you that when the gaseous metal is heated, it loses 1 electron, that is ionization, to give you sodium ion. So what we have here is now the ionization energy, IE, to move sodium from solid state to gaseous state, sublimation, enthalpy sublimation, to move it from gaseous state to ionic state, that is ionization energy required. And that takes care of the metal. We'll now go to the non-metal. The non-metal, the chlorine molecule, the first process we talk about was step number energy, or step number 3, which we call the dissociation energy, or the bond dissociation energy, whereby half molecule of this is converted to chlorine atom in gaseous state. So that is the bond dissociation energy. So we can write it as BD, bond dissociation energy of chlorine molecule. So the energy required to dissociate chlorine molecule to produce a free atom in gaseous state. That is the dissociation energy. Then after that, we also talk about what's called electron affinity, whereby the energy released when the chlorine atom or gaseous atom is converted to chlorine ion or chloride ion. We call that the electron affinity. You see that? So that the steps involved. So the metals undergoes 3 steps. from two steps sublime while in the enthalpy of sublimation, and then it ionizes to produce ionization energy. Non-metal also undergoes two steps dissociation from chlorine molecule to chlorine gaseous atom, and then electron affinity. So two steps in each case. So when we have done that, what then do we do? We now say we join this together. We draw an arrow from here and move to that point. The energy required, or the energy change when, let me get this thing off a little. That'll be better now. So the energy change or the energy release when 1 mole of a compound, ionic compound, is produced from, this is the ionic compound, sodium chloride, it produced from is gaseous ions, is what we call the lattice energy required, that which is representing the symbol L, the lattice energy. So this is the Born-Haber cycle. Now, for us to make it clearer, you see that the enthalpy of sublimation is positive value. The ionization energy is also positive value. The electron affinity is negative enthalpy value. The bond energy of dissociation is positive, while this one is negative. So this is an example or illustration of the Born-Haber cycle. Now, how do we apply this to solve problem under this? So, according to Hen's law, the major reaction is this one we have here. So this is the first equation, enthalpy of formation of sodium chloride. For it to form sodium chloride, it involves all these steps we have listed under it. So according to Hen's law, we can now say that delta HF, the enthalpy of formation, will now be the sum of all the energy changes involved in these processes. So that becomes enthalpy of sublimation plus ionization energy plus bond dissociation energy plus electron affinity plus lattice energy. So we'll add these four energies: sublimation, ionization, dissociation, electron affinity, and lattice energy. We're going to have the enthalpy of formation of an ionic compound. So in questions involving the Born-Haber cycle, you may be given all this and you will be asked to find the lattice energy, or you'll be given any of them and they ask to make one of them unknown, or you'll be given everything, you have to find the enthalpy of formation and so on. So you follow this process to solve it. So let's now take some questions. So let's look at the problem on the board that says use the information below to calculate the lattice energy of sodium chloride. I'll have the reactions there. The first reaction shows sodium going from solid state to gaseous state. We'll give you the enthalpy of sublimation as 107 kilojoule per mole. The second reaction shows electron affinity, sodium gaseous state going to sodium ion. Electron affinity is minus 502 kilojoule per mole. So the second reaction shows dissociation of chlorine molecule to two chlorine gaseous atoms. And we're giving the energy there as plus. This dissociation energy as 242 kilojoule per mole positive. Then we'll have the third one, chlorine atom gaining electron to give you chlorine ion. Electron affinity minus 355 kilojoule per mole. Then the fourth equation is formation of sodium chloride from its constituent elements. Have the enthalpy formation as 411 kilojoule per mole. We're asked to use the information to calculate the lattice energy of sodium chloride. From the Born-Haber cycle and the Hen's law of constant heat formation, we were given that the enthalpy of formation is given by the sum of other enthalpies, which include enthalpy of sublimation plus that ionization energy plus the bond dissociation energy plus the enthalpy 1 plus the lattice energy. So that's the information we gave initially from the Born-Haber circle. So before we continue, we want to substitute the values here and then make our the subject. The enthalpy of sublimation is 107. We have 107 there, equal to the enthalpy of sublimation is, okay, there's an error. Enthalpy of formation here is down there. Delta HF minus 411, sorry, equal to the enthalpy of sublimation. The value here is 107 positive value. The additional energy, the value is minus 502. We have that, plus the energy of dissociation. The value here is 242. I'll divide the 242 by 2, multiplied by half. Why did I divide by half? Because dissociation involves, if you go through the equations I provided, involves production of 1 mole of the atom. So this is the actual equation. 1 mole, but we'll have 2 moles of the atom produced. So it should involve 1 mole. So the bond dissociation energy is for producing 1 mole, but I'm having 2 moles here. So what the energy involved here is the energy used to produce 2 moles of the chlorine atom, but our interest is in producing 1 mole of chlorine atom. That is like half Cl to give us only Cl. So because we have 2 moles here, this energy is for 2 moles. We have to multiply it by half or divide by 2. Then plus our L, which is the lattice energy. So solving this out, what then do we have? We now have minus 411 equal to 107 minus 402 plus 241 plus L, because half times this give you 2. Okay, that'll give you 121. So half times 242 give us 121 plus L. We then solve and make the subject. Our L now becomes, crossing everything to this side, minus 411 minus 107 plus 502. Then minus 4, this crossing over becomes minus, this crossing over becomes plus, this one crossing over becomes minus. So we solve this, we get the lattice energy of sodium chloride. So there's an error in the equation that we wish to correct here. Please, the energy is positive value, not negative. It's positive, please. And that will make this one positive, not negative, please. We'll correct the mistake. And then, if you look at it, sublimation is there, ionization is there, dissociation energy is there, lattice, which you're looking for. Something is missing, we would not put electron affinity. So that should be, we should add electron affinity to the formula. So you go through it again. So the enthalpy of sublimation plus enthalpy of formation becomes enthalpy of sublimation plus IE plus dissociation energy plus electron affinity, then plus lattice energy. So 5 energies are involved in this step. 1, 2, 3, 4, 5. All of them will give you the enthalpy of formation. So let's substitute again. Enthalpy of formation is minus 411. Enthalpy of sublimation is 107, given to you here. Initial energy is 502, no longer negative, is positive. Then dissociation energy will multiply by half because of what I explained before. So we should be only 1 mole produced here, or 1 atom. So since it's 2 atoms, divide this by 2 to get that of 1 atom. Then electron affinity is there, should be added. So that should be minus 355. Electron affinity, then plus L. Then good. So having done that, so let's correct the error. Plus L. Then we now move and solve. We now have minus 411 equal to 107 plus 502. Multiply this, that give us 2121, half time, divide by 2. Then minus 355 plus L. So making L the subject, moving all the terms to this side. L now becomes minus 411. This one crossing over becomes minus 107. Crossing over becomes minus 502. Crossing over becomes minus 121. Crossing over becomes plus 355. So minus 411 minus 107 minus 502 minus 121 plus 355 will give us negative 786. So minus 786 kilojoule per mole. So this is the lattice energy of sodium chloride produced. So that is it. We'll take another example. So look at the next question on the board that says, use the information below to calculate the electron affinity of bromine. We're given the heat of formation of sodium bromide at minus 359.9 kilojoule per mole. The bond dissociation energy of bromine molecule as 192.4 kilojoule per mole. Lattice energy of sodium bromide is minus 736.1 kilojoule per mole. Heat of sublimation of sodium 109 kilojoule per mole. Initial energy of sodium 496 kilojoule per mole. So we have to calculate from the information, we have to find the electron affinity of bromine. So for the same formula we introduced before, for enthalpy formation using the Born-Haber process and the Hen's circle, again by enthalpy of sublimation, SUB plus the ionization energy plus the electron affinity plus the bond dissociation energy plus the lattice energy, all added together. Now, all the informations are given to us except that of we also find that the electron affinity of bromine. So we now substitute. The heat of formation of this is minus 359.9. The heat of sublimation or the substance is given to us of sodium, is given to us as 109. The energy of sodium is 496. The electron affinity is what we're looking for, call it EA. Then the dissociation energy, remember that is a molecule. So this is, we'll divide this by 2 as I did before. We'll find half of the energy given to you, they are 192.4. Then the lattice energy is given to you as minus 736.1 kilojoule per mole. So when we solve, we now have minus 359.9 equal to 109 plus 496 plus EA plus half of the dissociation energy. That gives us 9 divided by 2, 96.2, then minus this value, 736.1. So make EA the subject, carrying all the values to the other side. EA now becomes equal to minus 359.9 minus 109, then minus 496, crossing over, become minus, then minus, this is plus 96.2, this is minus, crossing becomes plus 736.1. So when we solve all this, the electron affinity of the substance will now turn to, will now become minus 325. So minus 325 kilojoule per mole. So you see how to apply the lattice energy. So for this dissociation energy, is the non-metal is the atomic. How to divide by 2? Well, if it's triatomic, like there's a S3 triatomic divided by 3 to use to apply the dissociation energy. Every other thing follows. So that is it. Having done that, we'll now go to covalent bonding. So before we go over to covalent bonding, let's look at metallic bonding. Metallic bonding. So metallic bonding. So what is metallic bonding? Metallic bonding is a type of chemical bonding that arises from the electrostatic attractive force between the sea of valence electrons, otherwise called electron cloud of delocalized electrons, and the positively charged metallic nuclei. Nuclei is plural form of nucleus. It accounts for the physical properties of metals, which include ductility, high melting and boiling points, conductivity, malleability, and so on. So as we say, it's a kind of bond which arises from the electrostatic attractive force between the sea of valence electrons or electron cloud and the positive charged metallic nuclei. Metallic bond does not occur in compounds. We're explaining it. It doesn't occur in compound, right? It occurs in elements. All kinds of chemical bonding occur in compounds or molecules except metallic bond, which occur in elements called metals. So every metal has metallic bond. Let's try to explain this using a simple metal like sodium. If I use sodium as an instance, we know that sodium, its atomic number is 11. So 281. If I have a piece of sodium, what it means that inside a sodium structure, there should be atoms of sodium close to each other. So all these circles represent the M shell of sodium, or the atomose shell of sodium, because bonding involves the atomose shell, as I explained at the early part of this tutorial. So we have this. So all these are atoms of sodium, all clustered in a piece of sodium crystal. Now, at the center of each atom is the proton and neutron, but what we represent is the proton, because the neutron has no charge. Proton, positive, 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 and positive. So what I'm trying to say now, in metallic bond, now each of the atomos, this is each atom of sodium, each of the valence shell has one electron in it. So in metallic bond, the electron found in the atomose shell of each atom does not belong to any of the atoms. Rather, these electrons wander or move around in the crystals, in the interspaces, interspaces between one atom and the other. So the interspacing between one atom and the other. So these electrons are the valence electrons of each atom wandering around. So we call this electron pool from each atom, which does not actually belong to one atom, but belong to the whole lattice, belong to the whole metal. We call it the localized electron or electron cloud. Electron cloud, or you can call it sea of valence electron. So valence electrons from each of the atoms is now part of the whole crystal. Rather, it does not actually belong to only one of the atoms. So the attraction between the positively charged protons or nuclei of the metals and this electron that constitute the electron cloud make up the metallic bond, because these protons are positively charged, the electrons are negatively charged. So there's bound to be attraction that will put the atoms all together. That's why a metal is always hard. The higher the number of valence electrons in the electron cloud, the stronger the metallic bond. So this is the concept of metallic bond, the bond that exists in atoms found in a metal. So all metals possess metallic bond. As I say, metallic bond accounts for the physical properties of metals, which include malleability, ductility, conductivity, and so on. So now we'll go to covalent bonding. So let's look at the key features of covalent bonding. So covalent bonding from the word cooperation between two or more things. So the first feature that we say, it involves sharing of equal number of valence electrons between non-metallic atoms. That means covalent bonding is normally found between two or more non-metals. So it's different from ionic bonding. Ionic bonding occurs between a metal and a non-metal. Then we will see that in covalent bonding, electrons are shared. It involves sharing of equal number of electrons. Let's go to number 2. Electrons are not transferred, rather shared. So in covalent bonding, electrons are shared, not transferred from one atom to the other. Number 3 point, the number of electrons contributed by each atom for sharing is equal to the number of electrons required by the atom to complete its atomose or valence shell. I repeat, the number of electrons contributed by each atom for sharing is equal to the number of electrons required by the atom to complete its atomose shell. For instance, look at oxygen. Oxygen is, atomic number is 8, have Kl26. Look at oxygen. Oxygen is the non-metal by virtue of having more than 3 electrons in the outermost shell. It has 6 in the outermost shell. A non-metal. Should oxygen combine with another non-metal, you're going to probably bring 2 electrons. Why would it bring 2 electrons for sharing? Because it requires 2 to complete its outermost shell. From the third point, the number of electrons contributed by each atom for sharing is equal to the number of electrons required to complete its outermost shell. So it needs 2. So if oxygen is undergoing covalent bonding with another fellow oxygen atom, it's going to bring 2 electrons because it requires 2 to complete its outermost shell. If I look at chlorine, another non-metal, 287. Chlorine requires 1 to reach the Octet state. So should chlorine combine with another non-metal to form a bond, chlorine will bring 1 electron, not 7. 1 because it needs 1 to become complete. So having done that, we said that covalent bonding occur mainly in non-metals. So what are the examples of substances that possess covalent bonding? Examples of substances that possess covalent bonding include so let's look at examples of molecules with covalent bonding. As I said before, covalent bonding occur in molecules or non-metals. The first example are homonuclear molecules. That is molecules that consist of similar atoms. Hydrogen H2, oxygen O2, chlorine Cl2, nitrogen N2, fluorine F2. So they all contain similar atoms in a molecule. They are gases, of course. Heteronuclear molecules. Heteronuclear are molecules made up of different elements. We call them heteronuclear molecules. So you can see water, hydrogen, and oxygen, the two are non-metals. Ammonia, nitrogen, and hydrogen, even though they are different, they are non-metals. NH3. HCl, hydrogen and chlorine, the two are non-metals. HF, hydrogen fluoride, the two are also non-metals. They are heteronuclear because they contain non-metals. Also, methane, CH4, carbon is a non-metal, hydrogen is a non-metal. Methane or hydrocarbons in general, they are all heteronuclear. They contain dissimilar or different molecules and they are covalent. Then number 3, compounds that contain less electropositive metals or metalloids and non-metals. That is, compound that contain metals and non-metals can still be covalent. Remember, as I said before, ionic compounds are those compounds that contain metal and non-metal. But there are also some compounds that contain metal and non-metal that are also covalent. And that metal there must be less electropositive. Example, aluminium is less electropositive, is in group 3 compared to group 1 and 2 elements. So aluminum chloride is covalent, beryllium hydride is covalent, boron chloride is covalent. Remember that boron is a metalloid. Silicon tetrachloride is covalent. Silicon is also a metalloid. So these are examples of covalent substances. So now we shall go ahead to illustrate covalent bonding. And before we illustrate covalent bonding, we're going to introduce what is meant by lone pair and bond pairs of electrons before we go to the illustration of covalent bonding. So as I said, before we go into covalent bonding, we have to understand what is meant by lone and bonding pairs of electrons. So the word lone, lonely, also known as unshared, or you call it non-bonding pairs of electrons, are the valence electrons in a molecule that are not used in bond formation. In covalent molecule, those electrons in the outermost shell of the molecule not used in bond formation are called lone pairs of electrons. The bonding or shared pairs of electrons are the valence electrons in the molecule that are used in bond formation. So let's look at that illustration of covalency in chlorine molecule. This is Cl2 formed by 2 chlorine atoms. Although we're yet to go to the illustration, but our interest now is to understand what is meant by lone pair and bonding pairs. Now you look at chlorine molecule, there are the 2 atoms joined together. Now you see that this dot is the electron from this atom. Asterisk is the electron from the other atom. So this bond is formed by this bringing this asterisk electron, this one bring this dot. So this electron that is being shared. So this one is called the bonding pair or shared pair of electron. Then in the outermost shell of the two chlorine atoms, you see electrons moving around them in each atom. These electrons here are not used in bonding. So this electron didn't join with these ones. So these electrons that are not used in bonding are called the lone pairs or non-bonding. So if I should count how many lone pairs are in chlorine molecule, you have two atoms in the molecule. The lone pairs, if I should count them, a pair it means two. 1, 2, 3, 4, 5, 6. So chlorine molecule possesses 6 lone pairs. 6 lone pairs. I repeat, those electrons on that each of the atom not used in forming a bond are called the lone pairs. 1, 2, 3, 4, 5, 6. 6 lone pairs. That means 12 electrons. Then how many bond pairs, bonding pairs are in chlorine molecule? This is a pair shared in between. We have 1 bond pair or 1 bonding pair in chlorine molecule. So in chemistry, it's conventional that when there's a bonding pair, that's where our interest is always in bonding. When there's a bonding pair, remove it and replace it with a slash. That slash means single covalent bond. Single covalent bond. You can see that. So you look at this molecule. This molecule possesses single bond. A single bond means 2 electrons shared or a bond pair shared. The lone pairs are not replaced with any bond. The bond pair is what replaced with the bond. So chlorine molecule consists of single covalent bond. If I use another illustration, for example, if I use oxygen, O2, oxygen is have this. Okay, let's use the bond. After we can then the bonding. 1, 2, 3, 4. It has 6 electrons atmosphere, so 2 of them come up here, and that 2 from the other atom come up there. So this is the nature of bonding in oxygen. Although we're here to discuss the bonding, but our interest is to identify the lone pairs and bond pair for now. Now this is oxygen molecule. Each atom having 2, 4, 6, 8. 2, 4, 6, 8. In covalent bond, the electron share belong to both of them. So 4 here, 6 and 8, Octet state certified. 2, 4, 6, 8 certified. Now, if you are looking at this molecule, oxygen atom is consist of these two molecules consist of 2 atoms joined together. How many bond pairs are in oxygen molecule? This is the bond pair or shared pair, under bond pair, a pair under pair. So oxygen molecule has 2 bond pairs or bonding pairs. Then how many lone pairs are in oxygen molecule? This one is the bonding. 1, 2, 3, 4. 4 lone pairs. And when I join them together, what kind of bond will I have in oxygen molecule? Oxygen now have a bond pair played by a slash, a single bond, and a single bond. So oxygen molecule has double covalent bond, double bond. How do I know that double covalent bond? So the double bond in oxygen molecule is the 2 pairs that are shared, or 2 bonding pairs. So you can see we have single bond, covalent bond, we have double bond, we also have triple bond. An example is nitrogen. If I come to nitrogen molecule, N2, 2 atoms, each of them having 5 valence electrons. So this is nitrogen for you. So nitrogen molecule. So you see the Octet state certified. 2, 4, 6 plus this 2, 8. 2, 4, 6 plus this 2, 8 complete. Now, question is this: how many bonding pairs are in nitrogen? The electrons that are joined together are the bonding pairs. 1, 2, 3. 3 bonding pairs of electrons. How many lone pairs are in nitrogen molecule? A pair here and that pair here. 2 lone pairs in nitrogen molecule. So having done that, what kind of bond is in nitrogen? So we'll now join them. So nitrogen has triple bond or triple covalent bond. So we can have single bond, double bond, and triple bond. So these are the 3 types of covalent bond. There are 3 types: single, when a pair is shared between 2 atoms; double, when 2 bonding pairs are shared; triple, when 3 bonding pairs are shared. So now we're going to now demonstrate or illustrate how covalent bond is formed, as we have on the board. So we're now going to look at illustration of covalency in homonuclear molecules. Let's take the simplest example, hydrogen, molecule that consists of two similar atoms. We split hydrogen the same way I did for any bonding into the two different atoms. Red electron configuration, one, atomic number of hydrogen is 1, of course, one in the case shell, one in the case shell. Both elements are non-metals, so they cannot donate to each other, because the bond here must be covalent because they are non-metals. You draw a Lewis structure, hydrogen for each other atom, this is hydrogen, one electron in the atomos shell, and that hydrogen atom, one electron in the atomos shell. Now, how many electrons does hydrogen require to become complete? Hydrogen requires one electron each to become complete. Because hydrogen, as I told you, the only element that satisfies duplet state in chemistry. So it needs extra one to make it up to 2, so it will look like helium. So should this one give one electron to this one to this, it becomes 2 and it will cheat itself, which is not proper. Or should this one give 1 to this, it becomes 2, it will cheat itself and become incomplete, which is not proper. So they're going to share, that's covalency. So as I told you, the number of electrons they're going to share is equal to the number they need to become complete. So each of them requires 1, 1. So they're going to bring 1, 1. So you now bring the elements together and then bring the 2 electrons at their close to them, at their middle. So you have 2 electrons. And in covalent bonding, the electron, the bonding pair or the electron share belong to both of them. So this one has 2, filling up the K shell. This other one also has 2, filling up the K shell. So in terms of the type of covalent bond, a bonding pair means a single bond. So hydrogen molecule has a single covalent bond. How many bond pairs? A single bond means a bonding pair or shared pair. How many lone pairs? There's no lone pair on hydrogen. So hydrogen molecule has 0 lone pair, but 1 bonding pair of electron. So having demonstrated that, so we can use another example like chlorine molecule, number 2, chlorine Cl2, Cl plus Cl. Each chlorine atom is 17, atomic number 287, 287. Now, then look at the bonding sequence. We draw the Lewis structure. The Lewis structure, each of them has 7 electrons in the shell. Have 1, 2, 3, 4, 5, 6, 7 valence electrons. This one is also 7. 1, 2, 3, 4, 5, 6, 7. So they both are non-metal because they have more than 3 in their atomos shell. That means they are going to accept electrons from each other. They will share from each other, please. They contribute for sharing, equal number. So what does this one need? This one needs extra one to become complete, to make it octet state. This one also needs extra one to become complete. And the bonding now, this is going to bring 1, since it needs 1. This one is going to bring 1. It needs also 1 to become complete, to get octet state. So now have the 2 atoms coming together. Electrons will now pair up at the middle, and then you now include the lone pairs. You see that? So that is a very simple task. So in chlorine molecule, as you can see, this count the electron, be sure there is octet state certified. This is 2, 4, 6, 8 for this. 2, 4, 6, 8 for that. So each of them having octet configuration. So we can still draw the chlorine molecule to show the kind of bond present, a single bond for a bonding pair. So in chlorine molecule, question is how many bonding pairs do we have here, and how many lone pairs do we have in chlorine molecule? Chlorine molecule has only a bonding pair or a shared pair. 2 means a pair. And lone pairs, 1, 2, 3, 4, 5, 6, 6 lone pairs of electrons, also giving us a single bond, a homonuclear molecule. I'll take another example of a homonuclear molecule. I'll take, for example, oxygen. Oxygen is the homonuclear molecule. So let's see the kind of bond that oxygen has, or how bond is formed in oxygen. So oxygen consists of 2 atoms in it. A homonuclear molecule is 8. That is 2, 6 for each. 2, 6 for that. So having done that, let's do the bonding. So oxygen has 6 electrons in the atomos shell. So the Lewis structure of oxygen atom is 1, 2, 3, 4, 5, perhaps 6 here. Another atom, 1, 2, 3, 4, 5, and then 6 in the atom shell. Now, they are similar atoms and they need equal number, just like the examples we are already taking. This one needs 2, you have the 2 unpaired. Or from here, it's 8 minus 6, 2. 8 minus 6 require extra 2, 2. So in covalent bonding, what they don't contribute, since they are both are non-metals of the same kind, is equal to the number. What they need for bonding is equal to the number they require to become complete. They need 2, 2, so they bring out 2, 2. So you now have this oxygen, have that, have this, have that. Now have that. So you can see that. So how many bond pairs are in oxygen molecule? At the question, 2 pairs are shared here. So 2 bonding pairs of electrons. How many lone pairs? 2, 4, 6, 8. 8 lone pairs. What kind of covalent bond do you have in oxygen molecule? Oxygen molecule has double covalent bond. Double covalent bond. Because of the 2 pairs that are being shared. Double covalent bond. I take another instance. I'll take nitrogen, one that has triple bond. N2 nitrogen. That gives us N plus N, 7. The number is 2, 5. I don't know if it's 7. That is EC is 2, 5, 2, 5. So now let's do the bonding. Nitrogen has 5 electrons. Draw the Lewis structure of each atom. 1, 2, 3, 4, 5. Plus 5, 1, 2, 3, 4, 5. So they have 5, 5 in the atomos shell. Now, how many electrons does each of them need to become complete? Each of them requires 3 electrons. 1, 2, 3. 1, 2, 3. 3 electrons become complete. So, since they need 3, 3, they also contribute 3, 3 because both are non-metals of the same kind. So, you now have N. So, 3 electrons will pair up at the middle here from this atom. The other 3 from the atoms will also pair up with this. So, you now have that. So the question is this: how many lone pairs do you have in nitrogen molecule? How many bond pairs? We have 3 bonding pairs. Electrons shared. 1, 2, 3. 3 pairs shared. And 2 lone pairs. 1, 2, 2 lone pairs. What kind of covalent bond is present in nitrogen molecule? Nitrogen molecule possesses triple covalent bond or triple bond. You can see that in the middle. Triple covalent bond in nitrogen molecule. You see, these are examples of homonuclear molecules and how to illustrate bonding in homonuclear molecules. Perhaps I use bromine, for instance, Br2. Perhaps you may not know the atomic number of bromine to start with. So it becomes difficult for you to deal with. But the atomic number may not matter here because bromine is a halogen. Halogen means it's a group 7 element. And it has 7 electrons in its atomos shell. So to draw the atomic structure of bromine, I may not need the atomic number. Since it's a halogen, I know that each bromine atom has 7 electrons in its atomos shell. Just like chlorine, iodine, fluorine, they are all in the same family, halogens. So plus also under bromine, have 1, 2, 3, 4, 5, 6, 7. So they all require 1, 1 become complete. So you can now join. You have Br. Electrons will be pulled together. Then you now have that. Have this. Have this. Have this. Have this. Have that. So for bromine, we have how many bonding pairs? We have a bonding pair or a shared pair. How many lone pairs? 1, 2, 3, 4, 5, 6. 6 lone pairs. You're like chlorine that we used previously, number 2 example. So what kind of bond is in bromine? Bromine molecule possesses single covalent bond in bromine molecule. So you can see this illustration and see that it's very simple. So in the next one example, we're now going to illustration of covalency in heteronuclear molecules. That is 2 or more non-metals of different kinds. Okay. Heteronuclear molecules, the first example I will take is methane, CH4, a hydrocarbon. So the 2 elements are non-metals, quite alright, but they're different kinds. So that would say it's heteronuclear. The bond between non-metals, whether they're of the same kind or different in covalent bonding. So let's break this into the component atoms. We have 1 carbon and 4 hydrogen atoms. So I write the electronic configuration of carbon 6. I have 2, 4. Hydrogen is 1 in the K shell. Now carbon, I'll draw the central element is carbon. As the central element, the one that has only 1 atom in the compound, will be at the center. So I present the Lewis structure: 4 electrons in the atmosphere. 1, 2, 3, and 4. The hydrogen will now surround it, 1 on each end. Hydrogen with only 1 electron by the Lewis structure. Hydrogen here also, hydrogen here also. In this bonding now, carbon requires 4 to complete its atomic share. So you're going to contribute 4 for sharing. Then hydrogen requires 1. So each hydrogen atom bring 1, 1 for sharing. So carbon 4 electrons is going to be shared between 4 hydrogen atoms. So divide the 4 electrons by 4. Since you're going to 4, you're going to be 1, 1. So you're going to give 1 to each of the hydrogen atoms. And they'll be pairing now. So now have C, hydrogen and carbon electron come together. Carbon and hydrogen together. Carbon and hydrogen together. The carbon and hydrogen electrons together. So you can see the bonding here now. So question can be, how many bonding pairs of electrons are in methane molecule? So in methane molecule, the bonding pairs are, look at them, 1, 2, 3, 4. 4 bonding pairs. How many lone pairs are in methane molecule? In carbon, there are no lone pair around carbon. On the hydrogen atom, there are no lone pair around the hydrogen. So 0 lone pair. Carbon has satisfied the Octet state 2, 4, 6, 8 around it. While each hydrogen has satisfied the Duplet state by having 2 electrons filling up the K shell. Then what kind of covalent bond is in methane? Methane possesses single covalent bond because each bond pair is a single bond. Single covalent bond in methane. Another example we want to use on heteronuclear molecules is water, H2O. Number 2, H2O. So in water, we have 2 hydrogen atoms and 1 oxygen atom. So if we should write the electronic configuration, hydrogen is 1 electron in the K shell, oxygen atom number is 8, 2, 6. So having done that, we now ask ourselves, the bonding now, we're going to draw a structure. Which element is the central element? The central element is oxygen. Why? Because it's the element that has only 1 atom in the molecule. The 6 electrons, 1, 2, 3, 4, it has 5 and 6. Then hydrogen, 1 on this side and the other one on the other side. In the bonding, since we have nonmetals involved here, even though they're not similar kinds, oxygen is the one at the center. It needs 2 extra electrons to become complete. 6 plus 2 is 8. While hydrogen that's about the duplet state requires only 1, 1 to become complete. And since oxygen is sharing the 2 it has with the hydrogen, so 2 hydrogen, divide these 2 electrons, you're going to share by 2 atoms. That's going to be 1, 1. So you're going to share in that way. Oxygen. So electron, hydrogen bring, oxygen bring 1, hydrogen bring 1. Hydrogen 1, oxygen 1. So you have that. So if you look at the structure of water, not actually the structure, the bonding in water, you know that water molecule has 2 lone pairs on top, on below and above the oxygen. 1 to 2 lone pairs or non-bonding pairs, and 2 shared pairs. And water also possesses single bond, because each of the bond pair is a single bond. I will not call it a double bond because they are not together. If these 4 electrons were between 2 atoms only, between here and this, 4 electrons between this and that, we would call it double bond, but they are separated in single bond. So, having done that, the next example I want to take is ammonia. Ammonia, number 3 is ammonia, NH3, ammonia. Let's look at the bonding in ammonia. Ammonia consists of 1 nitrogen atom and 3 hydrogen atoms. You see, I have N plus 3H. If I write the electronic configuration of ammonia, nitrogen Kl is 7, atomic number is 7. There is 2, 5, Y is 1. The central atom is nitrogen, the element that has only 1 atom in the compound. So I put nitrogen at the center and draw the Lewis structure. Represent the 5 valence electrons around nitrogen, then plus hydrogen here, hydrogen there, and that hydrogen there. So nitrogen being at the center, we're going to share out 3 unpaired electrons. So 3 electrons need to become complete to 3 hydrogen. So the 3 hydrogen will still bring 1, 1. So divide this 3 by 3. So giving that to 3, will be 1, 1 to each hydrogen atom. We now have this bonding sequence in ammonia. So you have that. You have that. You also have that. So that is it. How many lone pairs are in nitrogen atom of ammonia? Nitrogen has only a lone pair on top of nitrogen. How many bonding pairs? 1, 2, 3, 3 bonding pairs. So ammonia also has single bonds in its structure. Single bond, single bond, single bond, and a lone pair on top there. So that's the bonding in ammonia. Having done that, the next heteronuclear molecule I will take is carbon 4 oxide. Alright, it's called carbon dioxide. CO2, carbon 4 oxide. Let's see the bonding in this molecule. Now, if you break it, you have 1 carbon atom and 2 oxygen atoms in CO2. So you write the electronic configuration. Carbon is 6, that is 2, 4. Oxygen is 8, that is 2, 6 in oxygen. Now let's look at the bonding in CO2. The bonding in CO2, you ask yourself which of the elements is the central element, that is carbon, the one that consists of only 1 atom. So I'll draw carbon at the center, the 4 electrons, the Lewis structure, the 4 electrons in the atomic shell. The oxygen are by the size. So 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then we look at the central atom, the most important. We ask ourselves, how many electrons does it need to become complete? It needs 4 electrons because you have 4, requiring 4 to become up to 8. So you're going to bring out 4 to share between this and that. Now from that 4 you're going to bring out, divide it, you're going to share between 2 atoms, divide the 4 into 2. You have 2, 2 go to this one, and 2 go to the other one. So the bonding will now follow us. We have oxygen. So carbon will bring 2 electrons on this side, oxygen bring 2. Carbon will bring 2 on the other side, oxygen will also bring 2. We now have the bonding complete. Carbon survive the Octet state, 2, 4, 6, 8. Oxygen, 2, 4, 6, 8. This other one, 2, 4, 6, 8. Complete. So from that structure we have here, how many lone pairs of electrons are in CO2? CO2 has, there is no lone pair on carbon here, but there are lone pairs on 1, 2, 3, 4. 4 lone pairs. How many bond pairs are in CO2? These are the bonding pairs. 1, 2, 3, 4. 4 bonding pairs and 4 lone pairs. And CO2 also possesses double covalent bond on both sides of carbon atom. So having done that, we are now going to look at what is meant by bond order. So bond order refers to the number of bonding pairs of electrons shared between adjacent atoms in a molecule. Number of bonding pairs of electrons shared between adjacent atoms in a molecule. For example, we have done some bonding. Look at chlorine. When we did chlorine, we saw that 2 electrons are shared. That is 1 from each chlorine atom. So now the bond order, how many pairs or a pair is shared? The bond order of chlorine molecule is 1. So bond order of chlorine molecule is 1 because it means a pair is shared between 2 atoms of chlorine. Then another example we did today is oxygen. In oxygen, we got, if you go back to the bonding, we saw 2 pairs shared. 2 electrons from this and 2 from this. So 2 pairs. The number of pairs shared is 2. The bond order of oxygen is 2. The bond order of oxygen is 2. But look at nitrogen that we did today. We saw 3 pairs of electrons shared, 3 from each of the nitrogen atoms, 3 pairs shared. The bond order of nitrogen is 3. So this is how you count bond order. This is for homonuclear molecules. Now, if I look at HCl, for instance, HCl, Look at what the bond order of HCl. HCl is formed between two different atoms. The atomic number of hydrogen is 1. That's 1 electron in the atmosphere. Then the atomic number of chlorine is 17. That is 287. The Lewis structure of chlorine is 7 electrons in the atmosphere. So you have that. So bonding, this requires 1, this needs 1. So in the bonding sequence, you have this, all of them contributing 1 electron each. So what the bond order of HCl? So 2 electrons, a pair is shared. The bond order of HCl is also 1, meaning a pair of electrons is shared between the two atoms. Then going further, let's look at ammonia. Ammonia. We look at the ammonia structure today. We saw nitrogen, and then we have single bond here, single bond here, single bond, because electrons are shared here from one from this and one from that. So you can go back to the illustration that we use for ammonia. The bond order of ammonia is 1. Why is it 1? How do I count it? I'm looking at any two adjacent atoms, so a pair, or here a pair. Don't say it's 3 because these electrons are not all together, like in nitrogen, they're not in one place. So the bond order of nitrogen is a pair here, a pair here, even though it can be a pair occurring in 3 or 4 different places. Doesn't matter, the bond order remains 1. You see that? How we count bond order of a molecule. What of CO2? One would did bonding in CO2 got something of this nature. Double bond here, double bond here. This double bond means 2 pairs are shared here. 2 from oxygen and 2 from carbon. So what is the bond order of CO2? The bond order of CO2 is 2 because these 2 pairs are not concentrated at one place. They are in different points. So we just choose any 2 adjacent carbon atoms. 2, this and this. 2 pairs or 2 pairs of electron shares. So this is how we'll find bond order of simple molecules, homonuclear and heteronuclear molecules. So we'll continue from here. In this aspect, we're looking at the valence shell electron pair repulsion theory. The valence shell electron pair repulsion theory, VSEPR theory. This theory helps us to predict the shape of covalent molecules. So from the first point, we'll say this theory helps to predict the shape or geometry of a molecule or covalent molecule. Some covalent molecules have bent shape, some have linear shape, some have tetrahedral shape, and so on. So this theory helps us to predict the shape of covalent molecules. Then number 2, electron pairs around the central atom. Electron pairs around the central atom, which could be lone pairs and bond pairs, or could be only bond pairs. The electron pairs around the central atom of a covalent molecule repel each other to an extent where repulsion is minimal. So the electrons surrounding the central atom in the covalent molecule repel themselves to the point where repulsion becomes minimal. Then number 3 point, the greatest repulsion exists between lone pairs and bond pairs. The greatest repulsion exists between lone pairs and bond pairs. Why is this so? Because the lone pairs are delocalized around the central molecule. They are not bonded to any atom. So repulsion is higher between the lone pairs and bond pairs. And this leads to distortion. Distortion means bending or change of shape or distortion in the shape of molecules. So that is it. We're now going to look at the shapes of simple covalent molecules, how to find their shapes. First of all, we're going to look at those molecules that have no lone pair at the central atom. Look at those molecules that has no lone pair at their central atom. Look at the kind of shape they can have. Before we now look at those molecules that have lone pairs at their central atoms. So the first case we're having here is a central atom with 0 lone pair, but bonded to 2 atoms with the formula like AB2, where A the central atom and B2 are the 2 atoms bonded to it. So any molecule of this nature has linear shape or geometry. Example, BeF2. Look at that molecule. BeF2 consists of beryllium and 2 fluorine atoms. Beryllium is the central atom. Atomic number of beryllium is 4. That is 2, 2. Fluorine is 9. The number of fluorine is 9. That is 2, 7. Now, the bonding between beryllium and fluorine is covalent, not ionic, because beryllium, as mentioned, is among the less electropositive metals. So the beryllium will not donate, it's going to share electron with fluorine. So we have beryllium with 2 electrons in the outermost shell, according to the Lewis structure. But each fluorine atoms has 7 electrons, being a halogen in the outermost shell. So we have done this before, because easy for you to understand now. So you can see the bonding again. So each beryllium is the central atom. You're going to share 2 out to the 2 atoms. So divide this 2 by 2, that gives me 1, 1, 1 here and 1 there. So the bonding, the structure will be like this, Be. Now have fluorine share electron with beryllium. So you now have complete the lone pairs. Have this 2, 4, 6. We clean up this side for it to be clearer. If you look at it this very, very well, you see that the central atom has 2 bond pairs, beryllium, but no lone pair. Central atom with 0 lone pair, so there's no lone pair on beryllium. The side atoms can have their own lone pair, like fluorine here. If fluorine atom has 3 lone pairs, 1, 2, 3, 1, 2, 3, making a total number of 6 for the whole molecule. But our interest is that when the central atom has 0 lone pair, no lone pair, it bonded to 2 atoms. We have what we call a linear geometry. So the shape of this molecule will look like this: Be, single bond, straight. The bond angle is 180 degrees. The linear geometry. So when you have a central atom in a molecule bonded to 2 atoms, and the central atom has 0 lone pair, the molecule will have a linear geometry, bond angle of 180 degrees. Go to case 2. So case 2, the solution will have a central atom with 0 lone pair. A central atom with 0 lone pair bonded to 3 atoms. Formula AB3 has trigonal planar shape. A central atom with 0 lone pair bonded to 3 atoms with the general formula AB3 has trigonal planar shape. Example, boron trifluoride. Let's see how true it is. In this molecule, the bonding is between boron and 3 atoms of fluorine. Boron is the central atom because it consists of only 1 atom in the molecule. The atomic number of boron is 5. The EC is 2, 3. Fluorine is 9, 2, 7, being a halogen. So they draw the Lewis structure of boron. Boron is 1, 2, and 3. Fluorine is having 7 in the outermost shell by the Lewis structure. 1, 2, 3, 4, 5, 6, 7. And that fluorine here. 1, 2, 3, 4, 5, 6, 7. Let me put the 7th one here, okay? And that fluorine here. 1, 2, 3, 4, 5, 6, 7. Boron is a metalloid. As I said, when metalloids are bonded to non-metals, the bond is most likely to be covalent bonding. So boron will donate 3 electrons, or will share 3 electrons out to 3 fluorine. So since giving out this 3, it needs 3 out. So because giving out the 3 out, you're going to share the 3 to the 3 fluorine. That is, divide the 3 by 3. That will be 1, 1, 1. So you now have boron, have this, and that, 1 from fluorine, 1 from boron. 1 electron from fluorine, 1 from boron. 1 electron from fluorine, another 1 from boron. So you can have the bonding here. Now in this case, this molecule corresponds to this formula. It's not only when you calculate this formula, there are a lot of molecules that can have this formula, but they are not trigonal planar. Like ammonia has this formula, and corresponds A, B3. But ammonia is not trigonal planar. Why it is so? Because in ammonia, nitrogen has a lone pair on it. So we're talking about a case where the central atom has 0 lone pair. Look at boron. Boron has used the 3 electrons it has in the atmosphere for bonding, and there's no lone pair. Boron has 1, 2, 3, 3 bonding pairs and no lone pairs. So the central atom has no lone pair. It bonded to 3 different atoms or 3 atoms. That gives you what we call trigonal planar shape. If I should draw this shape, the structure of this shape, it will look like this. We have the structure of the that will give you B, fluorine, fluorine, and fluorine. That is what is meant by trigonal planar shape. And then the bond angle between one bond and the other for this molecule is 120 degrees. So any molecule that has trigonal planar shape, the bond angle is 180. While for the linear shape that we did before, the bond angle is 180 degrees. Go to the third case. Look at case 3. When the central atom has 0 lone pair but bonded to 4 other atoms. Example, methane or alkanes in general have tetrahedral shape or geometry. So central atom bonded to 4 other atoms, and that central atom will have no lone pair. Look at methane. Methane is formed between carbon and 4 hydrogen. Carbon is 2 cis. That is 2 cis. Atomic number is 6. 2 4. Sorry, that is 1. Then the central atom is carbon. Have 4 electrons around carbon. Hydrogen bring 1 for bonding. Another one here for bonding. Another one here for bonding. Another one here. So the central atom is carbon. Around the carbon, you have only bond pairs, 4 bonding pairs of electron, no lone pair of electron at all. So that gives you tetrahedral shape molecule. So if I want to draw methane structure, due to the repulsion between the electrons, the electron will shift. They will pair themselves around the central carbon. So we'll have this kind of shape for methane. That is methane. The bond angle of methane, or the angle between one bond and the other in methane, is about 109.5 degrees. So methane has a tetrahedral geometry. So having done that, we'll now go to another case, case 5 or 4. So look at case 4. A situation where the central atom has no or has 0 lone pair, is bonded to 5 atoms, gives us a shape known as trigonal bipyramidal shape. Trigonal bipyramidal shape. Example is phosphorus 5 chloride, or also known as phosphorus pentachloride. Let's investigate this. So look at PCl for the bonding sequence. Phosphorus is 1 atom linked to 5 chlorine atoms. The atomic number of phosphorus is 15. You write the electronic configuration, you have 285. Chlorine, you have 287, that is 17. Now, having done that, what do we now do? We now look at the bonding sequence. So phosphorus, by the way structure, has 5 electrons in the atmosphere. 1, 2, 3, 4. We have this one 5. And then chlorine has, each chlorine atom has 7 electrons in the atmosphere. We have 1, 2, 3, 4, 5, 6, 7. Another one. 1, 2, 3, 4, 5, 6, 7. Another one. 1, 2, 3, 4, 5, 6, 7. We need how many chlorine? We need 5 chlorine atoms. So what will now happen? You see that if you look at that structure, it appears that we have only 3. We have 3 unpaired chlorine atoms, but we need 5 chlorine atoms. So what do we do? So what's going to happen here is that these 2 paired electrons up here will unpair. That's what we call expanded Octet theory. Since to accommodate the 5 chlorine, the 2 paired one will now separate, unpair, each of them going with 1 chlorine atom. So now I have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So in the bonding now, what happens? Each chlorine bring 1 electron, first of all, so this will form a bond here. This will form a bond there. They come together. This will form a bond there. Single bond. This will form a bond. 1 from phosphorus and 1 from chlorine. These two also form another bond, one from phosphorus and one from chlorine. If you look at phosphorus at the center, the phosphorus atom there has no lone pair. It only has bond pairs. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 bonding pairs around phosphorus with no lone pair. So the central atom has a 0 lone pair bonded to 5 atoms around it. That will give you what we call trigonal pyramidal shape. Trigonal pyramidal shape. So let us now try to draw the shape of this structure and see the way it looks like. Trigonal pyramidal shape. So I want to draw a PCl5. I'll have P, chlorine, 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 and then chlorine. Then what is the bond angle in this shape? There are two angles we experience in trigonal bipyramidal shape. Two angles. Above the plane, the angle here is 90 degrees. We have 90 degrees. Here, below the plane, we have 120 degrees. So there are two angles in a molecule that possess trigonal bipyramidal shape, like PCF5, PBR5, and so on, PF5. Two angles, 90 degrees and 120 degrees. Go to the fifth case. So the sixth